Thanks. It's very nice to be here. I'm going to be talking about some work in progress with Phil Sod and Steve Schenker. Phil is a student at Stanford. Let's imagine that we have a black hole space-time here, and we're doing some kind of measurement outside it, measuring some field outside the horizon. Sorry, before I started, I wanted to make a comment that I don't think I have like 20 minutes worth of discussion here, and I will have to leave sort of shortly after my talk ends. So I hope that you guys will ask as many questions as you can during the talk, and yeah. Don't save them for the end, is what I'm saying. Okay, so we're imagining that we're pinging the black hole at some time, and then we're measuring the response at some later time. And a fundamental property of black holes that's intuitively clear is that this type of, the effect of this initial ping on later measurements is something that decays with time, basically because whatever you do to the black hole falls into it. And so what that means is that the black hole space-time gives us a prediction for a correlation function between these types of measurements, which decays with time, initially exponentially and then later by a power in many cases. Now, this is a problem because in a quantum system, we can write a formula for a similar correlator, not quite this one, but something closely related in this way as a trace in the Hilbert space of the quantum system. Z of beta here is the partition function, and I've split up the thermal density matrix into two factors. And then we have the products of these two field operators. So this is just a formula in quantum mechanics for a correlation function similar to this one. And we can write it out even more explicitly in the energy eigenbasis, and we get a double sum over the spectrum of the theory with these oscillating exponentials, and then the matrix elements of the operator squared. So this is the formula in quantum mechanics for this type of correlation function. And an important feature of any function of time like this is that it does not decay with time asymptotically at late time. Functions like this are called almost periodic or quasi-periodic functions, and they just don't decay to zero for large values of t. So there's a fundamental tension here between these two pictures if you believe that a black hole is a quantum system with a discrete spectrum. And this is a version of the black hole information problem that was, I believe, first discussed by Maldacena in a paper from 2001. It's sometimes referred to as Maldacena's version of the black hole information problem. But there's been work by other people on this subject as well. Now, this is the basic problem that we're going to be discussing in this talk. Or actually something closely related to it. So here's the correlator I just copied from the previous slide. And there's a very similar story that applies to a slightly simpler quantity, where we just pull out this part here, the sum over the double sum. Sorry?
You're assuming it's a closed system.
Yeah, so we have to make the black hole a closed system in some way, putting it in an anti-de Sitter space or otherwise having some kind of boundary conditions that make it a closed system. Mm-hmm. Sorry? That's not the problem that Hawking solved. No, well, no, but his calculation applies, variant of his calculation applies to black holes in a box. Anyhow, I could be doing it in ADS, or I could be doing it somewhere with some boundary conditions somehow. That part isn't terribly important. No, sorry. We're not discussing whether or not the black hole is disappearing. We're just discussing a correlation function on the black hole background. And actually, we haven't mentioned Hawking yet at all. I won't mention him, but so yeah, but I should be clear about the setup. So in order for there to be a tension between these two pictures, it's important that the quantum system needs to be a system with finite entropy, a system with a discrete spectrum of energy levels. And a black hole in asymptotically flat space is part of a system that is not like that, because it involves all the very low frequency, continuum of low frequency modes very far from the black hole, have nothing to do with the black hole at all. So basically what we need to do is get rid of that stuff. And one thing we can do to do that is put the black hole in anti-de Sitter space or some other kind of box.
But part of the price of that is that you, maybe jumping ahead, you no longer have the sharp form of
No, so that's why we have this form. Oh, okay, sorry.
From the information paradox that Hawking had, where something of order 1 becomes order 0, rather you have to look at exponentially suppressed corrections to correlation functions at 1 time.
Yeah, well, I basically agree with you. We could, though, go to very late times, and then it's an order 1 problem. But most of the time, it's an exponentially small problem. Yeah, so that's a good point, that this tension is between a quantum mechanics prediction for this quantity, which at late times, while not 0, is almost always very small. And it's a tension between that very small thing and 0. And that's a sharp tension. It's not maybe as sort of visceral as like the dictionary just didn't come out at all, but it's a sharp tension. Okay, so where I got to here was that we were going to consider a slightly simpler quantity where we just take the double sum over the spectrum of the theory, and we forget this matrix element, and we won't divide by the partition function. So this double sum can be written just as a product of 2 partition functions with complex beta. Beta is the inverse temperature, so we're just taking a double sum over the spectrum. And this quantity has basically the same story, that in a gravity approximation, in a naive gravity approximation, it decays to 0 at late times, but in any quantum system, it shouldn't. So, okay. We didn't really do much in going between these 2 steps. Now, here's a plot of some data for this type of quantity in a quantum system. It doesn't really matter which one. It's the SYK model. And it has some relation to black holes, but that isn't too important. It's just that this is a plot of this quantity on a log-log plot as a function of time. And there's two curves that are drawn here. The red one is for an honest quantum mechanical system, and the blue one is an average over many similar quantum mechanical systems. It's sort of a smoothed out version of the curve. And I want to draw your attention to 2 features of this curve. I think they're labeled. Yeah, okay. So this region is referred to as the slope. And basically, this is the part that's easy to see in a gravity description of this system. And it's decaying with time, and you can sort of picture an extrapolation where it decays forever. And that would be the naive gravity description. There's another contribution here, which is this ramp region, which the average value is growing linearly in time. It's proportional to t. But it's proportional to t, but with a coefficient that's of order 1. Whereas this guy starts out huge, of order e to the 2s, if s is the entropy of the system. So if we have a big quantum system, then this curve starts out very high up, it decays, and eventually it becomes smaller than this other curve, which has started very small and is growing proportionally to t, but with no large coefficient. So this is the competition between the slope and the ramp. There's also the plateau, which I'm not going to discuss in this talk. The only point I want to make about this curve is that although it came from, well, sorry, I guess I've made a lot of points. The only further point I want to make about it is that a curve similar to this is expected to be correct in a wide class of quantum mechanical systems. And in particular, this ramp and plateau structure is consistent with expectations based on random matrix theory. So, right, so I think I've made this point already. Yeah, the height of the plateau is e to the s. So this function up here is e to the 2s, and it's here, it's e to the s. And in this region, it's growing linearly. So the time where it hits the plateau is the time when a linear function proportional to t becomes of order e to the s, which is a time that's itself of order e to the s. Okay, so the question is, where do these parts of the curve come from in a gravity description? How does the black hole produce for you these parts of the curve? If we believe that a generic quantum system, including a black hole, should have a curve similar to this for this quantity, and we know how to describe this part, where do these pieces come from? Okay, so let me just review where the slope part comes from. So z of beta, the partition function at inverse temperature beta, is computed in gravity by a Euclidean path integral where the important saddle point corresponds to a Euclidean black hole, where the periodicity of the solution is proportional to beta. So in a two-dimensional theory, so two space-time dimensional theory, this black hole solution has the topology of a disk. It's like this blue region here, and the circumference of the disk is proportional to beta. And if we study z of beta times z of beta, we just have two separate copies of this, two different theories. Each of them have a description by this Euclidean black hole. If we want to study this quantity, which is the one we're interested in, then we can just find a simple saddle point that contributes where we analytically continue the betas in the two systems separately to beta plus IT and beta minus IT. T here, in this talk, capital T is a time. It's not a temperature. So this is the naive saddle point. And this thing explains the slope region. So as an example, for this two-dimensional JT gravity theory that Daniel Harlow mentioned, it's possible to calculate not just the saddle point contribution, but all of the perturbative fluctuations around it. You get this exact function. And OK, it's proportional to e to the 2s0. That's what makes it very large initially. But it's decaying like a power of t, 1 over t cubed. So that's this slope region decaying. And this contribution actually just decays for all time. OK, so now before I discuss a contribution that resembles the ramp, I need to make one technical comment, which I apologize for. But OK, in order to discuss the ramp contribution, it's convenient to switch what we're doing a little bit and study a type of microcanonical transform of this quantity z of beta plus it, z of beta minus it, where we integrate over beta with this exponential weighting. Exponential weighting has an energy parameter E as an argument. So this function here depends on E and T. Now, what does this do to our bulk analysis? Now when we're looking for a saddle point, since we're integrating over beta, we should also look for a saddle point in the beta variable. And it turns out the saddle point will be at beta equals 0. But the second thing we need to do is to impose the stationarity condition with respect to beta. And that will require that the sum of the energies of the two black holes we'll find should be E. So now we can sort of comment on the type of solution we're looking for. When beta is 0, we're looking for solutions which sort of look like, which have boundary conditions similar to these two disks. So Euclidean periodicity that was originally by beta, but has now been continued to IT and minus IT. So it's a Euclidean periodicity by amount IT, which means it's a Lorentzian periodicity. So we're looking for solutions that are periodic in real time. And on one side, it should be periodic by time t, and the other system should be periodic by time minus t.
So you said beta equals 0 is infinite temperature?
Yeah, but that's right. But the condition of stationarity with respect to beta here fixes the energy, and it fixes the energy to be something finite.
Are you really fixing that exactly, though, or within some?
Within the gravity approximation, we'll do exactly this. Now, for a...
You don't expect that to be totally accurate.
No, but we'll get an interest... You're right, but the gravity doesn't seem to know that. OK. So this is the configuration we'll discuss. And this discussion applies to any black hole geometry. So we take the real-time black hole geometry. This thing has a time translation symmetry, which goes forward on the right side and backwards on the left side. And the saddle point we're interested in is one where we just identify the green surface here with a red surface. So these are two different constant time surfaces. Yeah? I think so, yes. I think this is the black hole version of that, exactly. Of the... Yeah, but there's just one. But in the Gutzwiller trace formula, you are summing over a large number of periodic orbits, and you're dividing by a large factor. And you get something that's actually proportional to t. And here, it's like gravity does it with just one configuration, and doesn't have a large denominator. Sorry? No, even there, you would have to sum over large numbers of primitive orbits and divide by a large factor. Yeah, here there's just one. There's no like determinant factor in the denominator that makes it small. Okay, so that's right. So this is the type of thing. And we take the region between these identification surfaces, and you can sort of picture it like a double cone. But where the direction that's displayed here, the angular direction in the cone, is a real-time direction. So these things have closed time-like curves.
Should I be confused about whether or not there's some term in the action right at the
Yeah, you should. And there is not. And I can explain that in a moment. Okay, so there's a few things to say about this geometry. First is that the action is 0. So now that requires explanation of 2 points. One is that there's no singular term in the action coming from this tip here, which I'm going to defer for a second. The other point is that we have here two Lorentzian geometry, and the contribution from the action is purely imaginary, and it cancels between the two sides of the cone. So that's the reason that the action is 0 for this geometry. By the way, another way of saying the action is 0, another important point, is that the action for these two disks that we considered was proportional to each of the two S-naughts. It was huge. It gave a very large contribution to begin with. The action was proportional to minus 2 S-naught. Here we don't have that factor because if you think about it correctly, this space has the topology of a cylinder, and the Euler characteristic is 0, whereas it was 2 for the pair of disks, which is why we got 2 S-naught, and here we get 0 times S-naught. Okay. Now, there's an important point, which is that we get a factor of t here, and the origin of that factor of t is actually you can think of it as part of the one-loop determinant. It comes from a 0 mode with a compact volume. And the 0 mode is easy to explain. The problem that we started out with had independent time translation symmetries for the 2 copies of the system. And this solution that we're considering spontaneously breaks that to a single time translation symmetry, which acts as the killing vector on this geometry here. So we've spontaneously broken a pair of time translation symmetries to a single time translation symmetry. And so we should integrate over the exact Goldstone boson, which is associated to the broken generator. That thing has volume t, because that's the circumference of these circles. So we get a factor of t, which is consistent with the ramp. So now we have something with 0 action, so it's not proportional to any exponentials in the entropy, and it's proportional to t. So this is the right thing to give the linearly growing ramp contribution. Could you ask the question again? Sorry. Yeah, I just didn't hear. Well, this one just has it. We started out with a geometry that has this time translation symmetry. Are you asking why it's reasonable that such a configuration should be the right one, or?
Asking why this periodicity should be t.
Oh yeah. Okay. That's because so normally when we study the partition function as a function of beta, the boundary condition for the Euclidean path integral is that the circumference should be proportional to beta. Now we're studying, so that means that the geometry is periodic in the angular direction with a period proportional to beta. Now we're studying z of beta plus it, and we've argued from this microcanonical transform that the saddle point is at beta equals 0. So the periodicity that was originally by beta is now periodicity in a Euclidean direction by an amount it, which means a periodicity in the Lorentzian direction by t. So it's just periodic by a real time interval t. Does that answer the question? Okay. So this thing contributes a type of smoothed out version of the ramp, linearly growing and without any exponential prefactors. Now, there's something funny about the geometry, obviously, which is this tip. which is a fixed point of the identification. And clearly we need to understand that part better. So let's start by discussing Rindler space. This would be a good approximation close to the bifurcation surface, which is a fixed point. And everything interesting is happening in 2 dimensions, so we can ignore the other transverse space. When we compactify the time t, we have to say what happens at the origin, rho equals 0. And if we were to smooth this thing out in a naive way, well, this is at least one naive way, then we would find that it was actually singular as epsilon goes to 0. The curvature here would be proportional to a delta function. But we can determine the right regularization of this cone from the contour that we integrated beta over in doing this microcanonical transform. I don't have time to explain the details of this, but the conclusion from that analysis is that we should regularize the cone with an I epsilon like this. This comes from the fact that the contour in beta was a contour that's parallel to the imaginary axis, but with a positive real part. And this I epsilon is related to that positive real part. And anyhow, if you take this geometry, which is a smooth geometry, even if we identify time t, the curvature is exactly 0. And so this is an answer to Daniel's question about whether there should be some term in the action arising from the tip. It won't be there for the cone if we regularize it in this way.
And it's a cylinder?
It has the topology of a cylinder. Okay, so, and the last funny point, which is related to this, is that the partition function for quantum fields on this double cone appears to be completely well behaved if we define it using this I epsilon prescription. And then take epsilon to 0. So, okay, I'm finished now. Let me just emphasize a puzzle, which is that the contribution we're getting from this geometry looks like this blue curve here. It's a smooth function, just proportional to t. We're not seeing these wiggles. And, sorry? No, we're not seeing it stop. That's the second puzzle. But we have some ideas. In particular, Steve has suggested that there might be a family of solutions with higher genus. So we started with 2 disks. We have a solution with the topology of a cylinder. We could have a sum over connected geometries with higher genus. And the picture that Steve has in mind is that that sum will be a divergent sum. And the plateau will be like a de-Broglie effect in the genus expansion of that theory. Anyhow, that's speculative at this point. But you're right that that's a second problem. But this one sort of bothers me particularly because I wonder, yeah, I don't know how, I don't have in mind a good way of getting these wiggles. And it makes me wonder whether there's some way that the effective bulk theory we're using here could somehow secretly be describing a disorder average theory where the right answer would actually be a smooth curve. That should be the case for JT gravity. And, well, okay. So that's all. Let me stop there. Thank you.
So, I mean, as you know, there's been a suggestion that gravity is just, you know, an effective theory, and to see the actual black hole microstates, we have to include all the matter, or all the other fields in string theory, say.
Yes.
So maybe the wiggles come only when you include all the other matter degrees of freedom that the full theory has, and if you restrict to just the gravity, you get this,
Yes.
as you say, this disorder averaged.
I'm going to ask you to, we'll continue this,
Well, sorry, it's 2:55.
right, which is 25 minutes after you started.
But the talks are 3 talks in a 1.5 hour period, which means 30 minutes per talk.
No, it's 20 minutes plus 5.
But it does work out to 30 minutes per talk.
Okay, yeah.
It's only because I have to leave shortly after this. I'm really curious in the discussion.
Okay, so
Let me just answer this quickly. That I like the suggestion, but naively the way that would work is that if we study the one-loop determinant or interacting effects from quantum fields propagating on this space, that there would be some kind of singularity, and that would be resolved. That would result in the wiggles. But it actually appears that perturbation theory on this double cone space is very well controlled, especially at large t, and more or less projects all the fields into the vacuum.
Next time you should spend more time with the DHI.
Yeah, well, it's hard to, yeah, okay. Sorry, there were two more questions, but I don't want to,
I'm just a little confused. Let's see, so these wait time, the ramp and the plateau
yeah.
was in a system that had a discrete spectrum.
Yes.
But your cone goes out to infinity. Is that a system with a discrete?
Yeah, yeah, it
spectrum?
could be ADS2, or some ADS
Uh-huh.
black hole. That's a theory with a discrete spectrum.
I see. So so that metric gets corrected
Yeah, the
further
cone
out.
should blow up into some
Good.
ADS asymptotics.
Okay. But can you see it in the flat space too?
Yeah, you would have,
Are
so
you predicting there's a ramp in the flat case?
I wonder whether it could be the case that there's some type of, sorry, actually, there's an instability in the canonical ensemble, right? Canonical ensemble doesn't really make sense for the black hole in flat space, so I wonder whether there's some kind of negative mode or something for some of these solutions. Or.
Could be.
But you would like to say for a black hole in flat space that it's sort of almost like a quantum system that's coupled to some infinite system. And it could be that there's some kind of ramp for the quantum system if you could separate it from the infinite system.
Yeah, it'd be cool if you could see that.